this is on. Yes, okay, very good. Good morning, everybody. Welcome back. So we start the second day of our summer school with the second lecture by Mathieu.
Thank you. So good morning, everyone. So let me remind you of what we were doing. We were discussing density functional theory. And yesterday I explained to you that the goal is to replace an interacting problem by a non-interacting one. So let me remind you that we are looking at n quantum particles, and they solve this kind of equation, so minus Laplace plus v hj plus the sum w of x j minus xk psi is e n of v psi. Okay, so that's the interacting problem where v is the external potential, w is the interaction, and we want to replace this by a simpler non-interacting problem. The sum is just the v tilde, but with the first term, some tilde is e n tilde or v tilde, some tilde, and the constraints will be that the two e's are the same, and maybe I write the constraint, maybe I write here. So there will be two constraints. The first constraint is that the e n of v is equal to the e n tilde of v tilde, but that's really just some normalization because v is anyway defined up to a constant, tilde. And of course the second constraint is that the rho of psi is rho of psi tilde, which gives the name to the method density functional theory. So rho is the density, and so you want a non-interacting system that reproduces the interacting density. That's the goal. And of course, in practice, you will never know v tilde. You have to think that v tilde will be a function of v. You never quite know it, but then you invent some approximations, which we will discuss later on today. Good. And yesterday I explained to you that when v tilde exists in some natural spaces, then v tilde is actually unique. That's what I proved for you yesterday. So now I will describe for you a completely different, or maybe not so completely different, but a completely different presentation, which is due to Lewin. So Lewin's convex formulation. So to be clear, we don't have any existence theorem so far, which is a little bit strange. But there's no existence theorem. And so one way of getting existence will be to use convex analysis, and you will see the existence theorems are not so nice either in the slightly more general situation, but at least we have some. But they are quite weak. So this is the famous paper of Lewin in 83 that I quickly mentioned yesterday. And let me explain to you how it works. And so the main remark, so the main point, is that the En of V is concave in V. Right, that's a concave function of the potential. Why is it so? Well, because the energy, so the Hamiltonian, so let me remind you, we have a Hamiltonian Hn of V, which is this guy. Maybe I could do here. That's Hn of V. The Hamiltonian is linear in V. And then En of V is the infimum of psi, normalized psi, of psi Hn of V psi. So you see it's an infimum of linear functions, and so that's a concave function. I mean, of course, one way to see it is just to take V1, V2, and T. Okay, and then because it's linear, you have that the H n of T V1 plus 1 minus T V2 is just T H n of V1 plus 1 minus T H n V2. Okay, so the kinetic energy and the interaction, you can always put the T and 1 minus T for free. And then you deduce that for any psi, psi Hn of T V1 plus 1 minus T V2 psi, okay, is just equal equal to this, and so it's just larger than t times the minimum of that guy, and t times n1 minus t times the minimum of that guy, so that's just t en of v1 plus 1 minus t en of v2. And since you have this for all psi, then you get the concavity when you minimize over psi. Good. So because it's concave, it seems natural to look at its Legendre transform. Okay, so when you have a concave function, you can define the Legendre transform. So let me give of course we are in infinite dimension, but let's not worry too much. So let me give a name to the dual to V. I'm going to call it rho. So let rho denote the dual variable. We don't quite know what rho is, but soon we will know that it's a density. Okay? Dual variable to V. And so when you have a concave function, it's very natural to introduce f, which is the supremum over all v of en of v minus rho v. Okay, if you have a concave function, so for me, I'm using Legendre transform. So if I have a convex function, my Legendre transform is concave. If I have a concave function, my Legendre transform is convex. I have two Legendre transforms, which sends convex to concave, concave to convex. Okay? So maybe I should remind you quickly of Legendre transform. Maybe it's easier if you start with convex. So imagine you have an f from R to R that's convex. So there it is. Like that, it's a convex function. So what is it that you do? Right, so if you have a convex function, then you define the Legendre transform. I don't know where to put the star, maybe I put it here, because I have two Legendre transforms, but it doesn't matter. So the f of y is the infimum. I'm going to mess it up, because I don't know what's correct. F of x plus x dot y, since you are in RD. Okay? So if you have a convex function, you define f star of y, which is that guy. And this guy is now concave, right? Because it's an infimum of linear functions. So what is it that you're doing? You see, you see so if I fix y and I look for which x it's obtained, I will get that f prime of x must be equal to minus y. So for any y, what I fix is the slope. So you fix the slope, which is minus y, and then, so this slope being fixed, you try to find the point where it's tangent. Okay, so the slope is minus y, and this is equal to a certain f prime of x, and there it is x. Then you place your slope exactly touching the curve, and then here is f star of y. Okay. And now just from this definition, you get a concave function. And when you have a concave function, you can also define another Legendre transform with a soup and a minus. And then Legendre, the theory of convex functions tells you that the star is f. Right? So Legendre Frenchel duality. And somehow it's very natural when you look at this picture. So here it says that the f of x is actually the soup over y of f star of y minus xy, okay? Which you see on the picture, you see, because what's that? This guy is just all the lines which are below. And it's going to touch the curve exactly for the corresponding y, and so you're just writing that a convex function is the supremum of all the slopes that are below. Okay, so now we do the same in infinite dimension. So we have En of V, there it is, that's our En of V, the ground state energy, it's concave. And so we introduce this function here, which is the Legendre transform. And so by a similar result, we think, we hope, that it's going to be true. Okay, so by the Legendre function duality, we will have the converse thing that E and V will be the infimum of the rho of f of rho plus rho v. Now it's something that looks quite good, because you see we have written our minimization problem of our n-body states in terms of a minimization problem in RD, where the variable is rho. Okay, so with this, we've decreased a lot the complexity. Okay, that's a minimization problem. For a function rho, which is defined on RD. Okay? Of course, we don't know the f, but this we will discuss later. So, if we knew f, then we've decreased a lot the complexity of the problem. So now we want to know what is f, and maybe what is rho. I mean, is rho a density? The answer will be yes. But, so there are things we can see easily. So first, let me remind you that the En of V plus C is equal to En of V plus C times N. Yes? Yeah. So there's the Legendre transform of the physicist, which is used mainly in statistical mechanics, where convex goes to concave, concave goes to convex because it's more natural. And there's the Legendre transform of in math, where convex goes to convex. And then you have to reverse the signs. You put instead of int, you put a soup, and then you reverse the sign. Okay? But I mean, no worries. If you write everything, you will see this guy is convex, and everything you want. Okay, so let me remind you that if I shift my potential, the energy is shifted by C times N. Okay? And now if you think 2 seconds, you will see that necessarily this implies that my rho has to have integral rho equals to N. Okay, so I have to remind you, when you do Legendre transforms, the Legendre transform is convex, but it can be plus infinity. This is allowed. So I'm telling you, if the integral of rho is not N, then it must be infinite. And I have another property that En is actually monotone, in the sense that En of V1 is less than En of V2, if V1 is less than V2 pointwise. And if you think 2 seconds, that will tell you that rho has to be a non-negative function. Okay? So that starts to sound good, right, in a way. So f of rho, finite, when defined, so that implies that rho is a non-negative function integral B N. And so rho really looks like a density now. We want to know if it is a density. So this is what Lee did a long time ago, 40 years ago. And so to identify F, we need to work with mixed states. We have to forget the idea of knowing exactly the quantum state. We just put the probability over quantum states. Anyway. So we work with mixed states. So let me remind you that if you have a Hermitian matrix M equal to M star, just a matrix just for. So you know that lambda 1, the lowest eigenvalue, is of course the minimum of x mx, or maybe v and v, with v equal to 1. The norm of v is equal to 1. Okay, so that's what we are using here. Right? We say that the minimum of the spectrum is obtained if I minimize over all size. Okay, but it turns out that this you can also write as the minimum of the trace of m gamma. Okay, you see, if gamma is a rank 1 projection, then it's equal. Okay, but the whole thing is that this is linear in gamma, And so when you minimize a linear function, you may as well work in the convex hull of rank 1 projections, which is just the set of gammas which are self-adjoint, non-negative, and trace equal to 1. Okay, so if you just write that any such gamma is just a combination of rank 1 projections, so you diagonalize gamma, you will see immediately that you have this formula. So it's a much bigger set, but the minimum is the same. Okay? And so such a gamma, you have to think it's a mixed state, so you can write gamma as a sum of ni with the idea. Okay, with the sum of ni is 1. So you have to think that the ni's are just some probabilities over some states, vi. And then, writing it like that, diagonalizing gamma, you get this formula. So we are going to do the same. We will be in infinite dimension, but no worries. So we conclude that E and V can also be written as the infimum over gamma, self-adjoint, or negative trace 1 of the trace of H and of V gamma. And now, we will again pull out the part involving V. Okay? So we have to compute what's the trace of the sum of the V of xj, j equal 1 to n gamma. And this is, of course, the integral of V times rho gamma over RT, where by linearity, where rho gamma is the sum of ni, the rho of psi I, and if gamma is the sum of ni psi I. Okay, so when we have a mixed state, we also have the density, which is just the average, the convex combination of the densities of the corresponding eigenfunctions of gamma. Good. So now I can continue some of the calculations here. So E and V, I can write as the infimum over gamma, where is gamma equal to 1, as the following. So I will have, of course, the trace of the Hn of 0, gamma, so the part which is just kinetic plus interaction, no potential, and then I put here rho gamma times V. Okay. And now the trick is to do what's called a constraint search. Chemistry. So instead of minimizing over all gammas, we are going to do two minimization procedures, one after another. So instead of doing the infimum over gamma, we will first fix the density, minimize over all gammas having this density, and then we minimize over the density. Okay, so here I can write this as the infimum over rho, or the infimum over gamma, with the rho gamma is equal to rho, of the same thing. And the whole point, of course, is that if I know that rho gamma is rho, then this term is just integral rho v. And so I conclude that E over v is equal to the infimum over rho of the infimum over gamma, rho gamma equal to rho, of the trace of H and of 0 gamma plus integral rho v. Now, you see, this function here, now it has really the same form as the Legendre transform that I had here. Okay, so this led me to suspect that f of rho is just this function over there. The whole point is that this function here is convex. It's an easy exercise, and this is where mixed states are very important. If you do the same manipulation with a psi, it does not work. Right? Because as a function of psi, it's not convex. But if you see it as a function, it's a function of rho, but here you have a function of gamma, so it's you're minimizing some linear functions with a linear constraint, you get a convex function. Okay, so this is convex in rho. And so you see, this says that this guy is the Legendre transform of this function. And so the Legendre transform of that guy must be this function because it's convex, but that's f. And so the conclusion is that f of rho must be, or if you like, we define f of rho like this, and then I will state a theorem that all the other things are valid. So f of rho, we define it as the infimum over all gammas, mixed states of, maybe I write it, so the trace, and then I have the kinetic energy, just to insist. Then I have the interaction, and then I have gamma. So we introduce this functional. Okay? This functional gives you, so you give yourself the density of your n-body system, and then it gives you the lowest possible kinetic plus interaction energy that you can have once the density has been fixed. Okay? This is called the Lib universal functional. Why is it universal? Well, because it doesn't depend on V. Right? So if you look at electrons, for instance, then T is equal to 3, W is 1 over X, 1 over the distance, and then f of rho is defined for any rho. Okay, so it does not depend on the situation in which you put your electrons. Okay? But this works for any, it works for bosons. Of course, all these calculations you can do for bosons and fermions, so there is a symmetry constraint hidden everywhere, and you can do it in any dimension, and you can do it with any interaction potential. Very good. And with this definition, it's clear that we have this property, which is written here, this property here. But what is not so clear is that you have this property, now, because first I use the Legendre transform, but we are in infinite dimension, is it really working? So this we will check. But because of what I did here, it's clear that if I define f that way, then I have this formula here, which is exactly that formula there. And so it tells me that I can, if I knew f, which I don't, but if I knew f, I could compute my very complicated n-particle minimization problem in terms of working only with a density rho. Okay? And if I knew what this f is. Of course, we will never know what f is, that's not the whole point, right? Because computing f is at least as hard as computing e. Okay? But what we will do is, somehow what we are trying to do is to find an approximation of E, that's the whole point. But instead of approximating the function E, we will approximate the Legendre transform F, and then by taking another Legendre transform, which is written here, somehow we will get a simpler model. So the idea is the following, so you have here En and V, which you see as a function of V, then you go to the Legendre transform, so you get this function F, and instead of trying to approximate this, what you do is first you take the Legendre transform, then you will do an approximation here, replace this by something else, right? By some f of rho. And then of course you can go back and you will get a corresponding approximation for V. Okay. And it turned out that it was much easier to invent efficient approximation for F than efficient approximation for E. Okay, so that's why, that's the general spirit of DFT. Okay, so now let me discuss a little bit these F properties, simple properties of F and duality. So let me justify what I told you, which was a little bit vague. So we define F like that. Okay, so that's the definition of F, and I'm going to justify everything I said. Maybe the first question is when is this defined for which rho? Okay? And so let me assume again that W is an NP plus O infinity, with P equal 1 in 1D, P is equal to the other one in 2D, and P is going to be able to in dimension 3 and higher. This is so that W is infinitesimally form bounded with respect to the Laplacian. Let me write it like that. Okay. And so you can always control the interaction by the kinetic energy. So you conclude that for every epsilon positive, there exists a constant, which depends actually on n as well. Let me not worry about the n dependence, we do it at fixed n. Okay, such that you can compare your Hamiltonian, okay, Hn, no V, just kinetic plus interaction. You can compare it in terms of just the Laplacian. So 1 minus epsilon, the Laplacian, let me write Laplace, right? So it's the Laplace in RDN. And then minus constant, and then you have a similar upper bound. Okay, good. So, of course, this F depends on W. So if I remove W, then I get a different F, okay, which I'm going to call T. So introduce the lowest kinetic energy of n particles in the mixed state of given density rho. Let me call it T of rho. Okay, so it's the same definition. Let me write it. So the integral over gamma, with gamma is equal to rho of the trace sum minus Laplace x gamma j equal 1 to n. Okay, so that's the lowest kinetic energy. Same definition, but when I remove the W. And so you see that this inequality here tells you that the F of rho is comparable to T. Okay, so you have 1 minus, because actually when I minimize over gamma, I fix rho, so I conclude that they are comparable. And so we were wondering for what kind of rho this is well defined. We conclude that W doesn't matter. Okay, so we conclude that F is going to be finite if and only if T is finite. So now we concentrate on T. We remove the interaction and we just look at the kinetic energy. And so the question is, when is T finite? So that's a small lemma. So first, for bosons, it's very easy because we know T exactly. T of rho is equal to square root rho and the kinetic energy of square root rho. So it's finite if and only if one. And for fermions, this is not true anymore, but there is a lower bound. And there is also an upper bound. Actually, the upper bound is a constant, not here. Okay? And so the conclusion is that T is finite if and only if rho, square root rho is an H1. It's maybe not a big surprise, the kinetic energy is like an H1 norm, but for psi. Okay? And it's saying that it's sufficient that square root of the density is set within H1, so that we can find a psi or maybe a gamma, which has this rho, and for which the kinetic energy is finite. Okay, so this is the natural class of rho. So the natural class of densities Okay, so they are of course the row are negative, integral row is n, and square root row in h1 of Rd. Let me remark that it's actually a convex set, because the square root of, the gradient of the square root squared is a convex function. Okay, so proof of the lemma. So the lower bound is what's called the Hofmann-Osterhof inequality. I think it's from 81. And it's just Cauchy-Schwarz. I mean, it's an easy computation. Okay, so let me remind you that rho of x is n times psi of x, and then x2 delta squared dx2 delta. And so we can first compute the gradient of rho. We assume we can compute everything, and then we compute. So we compute the gradient of rho, and we get 2n real part of psi of x delta bar psi of x delta bar dx2, and so on. And then we do Cauchy-Schwarz. Okay, so we do Cauchy-Schwarz here. And we conclude that the gradient of rho of x can be bounded by 2. Okay, we put an n with each, so we will get 2 square root rho, and then the square root of the bar of psi of x, x2, delta squared, 1 half. Just by Cauchy-Schwarz. And of course, the gradient of rho is 2 times square root rho, the gradient of square root rho, so if you simplify by square root rho, you conclude, maybe I continue over there. So we've just proved that the gradient of square root rho square of x, so it's bounded by the n times the gradient in x1 of psi of x, x2, delta squared dx2, delta dx. And so now you see if you integrate, and this does not use any symmetry of psi, I mean maybe of psi squared it does. So you see that if you integrate, you get immediately that gradient square root squared is less than the kinetic energy of psi and the full kinetic energy in all variables. And then if you write the same with the gamma, you can use the complexity of this term, and you get the inequality for mixed states as well. The upper bound. So for the upper bound, we need just to construct a trial state. So that's easy. So for bosons, we take IID particles. So namely, we take psi, which is square root rho over n, tensor n. And then when you compute, you find out that the kinetic energy of psi is just exactly 1 square root rho squared. Okay, you don't even need a mixed state. So then you must have equality. And for fermions, it's a little bit more complicated. Actually, tomorrow I will discuss much better inequalities than the one I stated. But the inequality I stated is due to Harriman and Lieb. And so it's a bit more complicated. So you see, you take a row with square root rho in H1, and you want to construct, and it's a pure state thing. Okay, so you want to construct a psi, which is anti-symmetric, which has this rho and has a finite kinetic energy. Not so easy. And so we are going to take a Slater determinant. Okay, so namely psi will be some U1 transferred at UN. And then rho is the sum of the uj squared. And so we will just pick the uj's to have modulus rho. Right. So the idea is the following: we take uj to be square root rho over n as we did for bosons. But now we have to make them orthogonal to each other, right? Because they are fermions. So they have to be orthogonal, and so we need to put a phase. So we e to the I theta j of x, and the phase is x dependent. Okay? And we need to choose the phase so that these guys are orthonormal. Not so easy if you think about it. But Harriman and Lieb, they solved it a long time ago. And so the trick is the following. So you take theta j of x, which is actually only a function of x1. So what you do is you do 2 pi of, now we mess up, but I think it's j over n, and then the integral minus infinity to x1, and then the integral over rt minus 1 of rho. Okay. So why is it working? See, when you compute uj and uk, so you get rho over n, and then you have e to the I2i pi j minus k, and then the integral minus infinity to x1, and then rho. And so you see it's of the form, so the trick is just, so dx2 and dx1, dxn. And so you see up there it only depends on x1. And so you can integrate over x2 and so on. So let me introduce f of x1, which is the integral of rho of x1, x2. Sorry, dxd. The notation is not so good. We are in t dimension. So dx2. I mean, these x's are not the same as the xj's, but I hope you, maybe I put the indices up. It's okay, we are in RT. Okay. And so there you go. Or should I integrate? Maybe I integrate minus infinity to x1. Okay, and then you see that this guy here is really 1 over n. The integral of f prime, and then e to I pi j minus kf. And so if you integrate, you will get exactly 0. Because this is going to be, I mean, the integral would be exactly 1 followed by 1 over n. The integral up there will be exactly 1, so you will exactly get e to the 2i pi minus e to the 2i pi, and you get 0. Okay, so that's one way to make functions orthogonal using only a phase. And then you need to compute, the kinetic energy. And in the end, you do some estimates, and you get the upper bound. Okay. And I will go back to the kinetic energy tomorrow. For today, that's enough. So now let me state the main theorem about... so now we know for which rho this is always defined, whether it's f or t. And let me state the main theorem which gives some properties of f and t. And let me link these properties to DFT, to what we want to do. So it's the following theorem, Legendre and Locality. Okay, so you take rho, a negative function with integral equal to n and square root for h1. We take W in p plus L infinity with the same p as usual. So the first thing is that what was written here on the board is true. So the f of rho is actually the sup over v of E and of V minus rho V. And the only thing I have to tell you is for what kind of V, and so we're going to assume that V is in LP plus L infinity with the same conditions on P. Okay, so it's just telling you F is the Legendre transform of its Legendre transform, that was E. So everything is fine. And it works as in finite dimension. If V realizes the above sup, so if the sup is attained, yes, take the same, yes, let's not worry. I mean, it doesn't have to be the same. But my P, no, sorry. It's only in dimension 2, right? In dimension 1, I told you P is 1, in dimension 3, it's the other 2. So then it's fixed. Dimension 2, somehow you can take any P strictly bigger than 1, and then it could be different for W and V, but let's not worry. Take the same. Okay, so if V realizes the above sup, let gamma be, oh yeah, I forgot to tell you. Maybe I do it first. Maybe I do it here, sorry. There always exists a gamma, okay, so if you fix a rho, then f of rho is the minimum over all gamma, so there always exists a gamma realizing, so minimizing for f of rho. Okay, so you pick a rho, then I'm telling you there's always a gamma that will solve this minimization problem here. Or there if W is 0. Second thing, the Legendre duality is correct, namely f of rho is the supremum over all potentials of En of V minus rho V. And third thing, if this supremum is attained, which is not so clear, but if it is attained, okay, then we take gamma minimum for f of rho, take any minimum for f of rho which exists, then gamma is the ground state for En of V. Okay, so I'm telling you, so you take a rho, you always know that there is a gamma, okay, which minimizes f of rho, very good. And then you ask yourself, is there a V? Is there a potential which solves this sup? And I'm telling you, if there is such a potential, then my gamma, which I found, must be a ground state for that V. So you see, it's really something having to do with duality. You fix a rho, then there is a certain gamma, and then if you find a potential, then this gamma is automatically a ground state for V. And so now the question is, when is this sup attained? And this is what's not so well understood, and we discussed, but we can say that the set of rows for which the sup is attained is that okay, so for most densities, and it's true that there will be a V. Okay. So maybe it's time to, not stop, but summarize the situation. Okay. So this theorem I stated for F, but in a way we actually need it for W equal to 0. So let me remind you what we want to do. So we want to start with a V and a W. Okay, and then we solve the problem En of V. And we find a certain ground state gamma. and we compute its density. Okay, you start from a V and a W, you compute the density of, say, one ground state. Let me remind you what we want to do is we want to find a V theta which has with no interaction, such that there exists a ground state gamma tilde which has the same density. Remember, that's the problem which is over there on the blackboard. Now we do for these states, but it's the same as the one on the blackboard. We have the interacting problem, we have the non-interacting problem. And so, for the first part, I have nothing to say, but the first part, what it does is to provide me a density rho. So now I have a rho, and I'm asking if I can find a V theta that will just reproduce this rho. And so you see, it's exactly this theorem, but for W equal to 0. I stated the theorem for any W, because it's the same. But we actually need the theorem for W equal to 0. And we apply the theorem for the density that comes from V. Okay? With rho equal to the ground state density coming from V and W. And so if you read again this part here, so this part is telling you that if you can solve this soup, then you have actually solved the problem. You found a guy, which is gamma, which is a ground state, which has density rho, and is a ground state for V. Okay? But we need this only for T. Okay, so let me rewrite this part here. Okay, so if there exists a V theta solving the following soup, so the soup of E and theta of maybe I call it W minus rho W, soup over W. So if you can find such a V theta which solves this soup here, then you conclude that there exists a gamma theta with rho gamma theta is rho, and which is a ground state for the non-interacting problem. With potential V theta. Okay, so maybe I rewrite again the same thing. So let me remind you that it's the non-interacting problem. So for fermions, we know what it is. It's just the sum of the n first eigenvalues. So if you like, maybe I write it here. So V theta, what is it? It's the argmax of the sum of the lambda j's minus Laplace plus W minus rho W. J rho. Okay, so if there is a maximum, I mean if the max is attained, then I take any point where this is attained, and that's the problem I have to solve, where rho is the ground state density for V and W. So we found a variational characterization of this potential V theta. And it's not only variational, it's actually, you have to solve this soup, so it's actually a concave function that you must maximize. So it's not only variational, it's a concave problem. So numerically, if you discretize, it's actually quite easy. Of course, you are in big dimension, so on and so forth. But if you give me a reasonable rho, okay, then you discretize, and it's not difficult to find approximate potentials in a discretized space. In infinite dimension, there will always be a maximum. Okay? And then it's not so difficult to find the potential that will reproduce that rho. So now you should complain and tell me, but you're crazy. No, you don't complain. Because let me remind you that the whole thing was to replace the interacting problem by a non-interacting one. And so here the only thing we are doing is just to try to see if it's doable. But we never really say how to do it. Because I'm telling you, if you know rho, then you could do that to find v theta. But of course you don't know rho, because if you know how to compute rho, then why would you do this whole stuff? Okay, so far it's just a proof of concept. And for chemists, it's been very important to know that in principle, it's possible to replace the interacting problem by a non-interacting one, and you would have to solve this problem for a density rho. Of course, they don't know rho, but then you will have to find approximations, and this is the next step. So it's an open problem to understand the class of rows for which this soup is a thing. And I'm just talking about the non-interacting problem. And of course, you see, it's not quite a proof of concept, because I start with an interacting problem, I get a density rho, and then I want to solve this problem. But how do I know that the rho is in a good class? But that's because I don't know the class of rows for which I can solve this problem, so for which there is a soup. And the theorem tells me it's dense. But dense doesn't mean anything, because you can be dense and be very small. Think of rationals in the real life. I mean, it's dense, but it's tiny. It's a zero measure. So that it's dense is not so useful. Okay, so it says, well, I mean, probably you can do it, but we don't quite know, and we're not so sure. Okay. But anyway, so let me continue. And so it's really wide open to understand what's a good class of densities for which you can solve this problem in the non-interactive case. It's purely a non-interactive problem. Let me take 5 minutes to, I think I want to keep this. I would also like to keep this, but maybe I given. Just quick elements about convex analysis. So how do you prove all this? So just 5 minutes. So you have a convex function on a Banach space. Okay. And it can take the value plus infinity, and we will assume that it's lower semi-continuous. Very good. And then, so let me remind you that it's a sub-differentiable. So the whole point is that the existence of V is related to F being sub-differentiable. Sub-differentiable if there exists an L in the dual, such that F of Y is always larger than F of X plus L of Y minus X. Okay, and this guy is just a slope which is below F of X, which I had on my drawing. So you're just asking if you can find a hyperplane below, touching the curve, below exactly at the point F of X. And the claim is that if L exists, and there could be many L, I mean, think a convex function can have jumps in the derivative. Right? So it could be several L's. But if L exists, then you see, I put it on the other side, and I find that the inf over y of f of y minus L of y is larger than f of x minus L of x. But this inf here is exactly f of L. Okay? And so I've proved that f is less than the Legendre transform. Where is the eraser? Ah, here. But on the other hand, we know that f is actually equal to the soup, so if it's less, then it's equal. So this implies that L maximizes the soup over L prime, if you like, of F star of L plus L of X. Okay? Which is equal to F of X. So I'm telling you that if there is a subdifferential, okay, then it's a maximizer. So the only thing we are asking here, so I'm just reformulating the existence of V. Okay, so saying that there is a V is just saying that we can find a hyperplane below the curve touching the curve, which is a kind of derivative of F. That's the only question. And so what's known in theory, what are the abstract results about the existence of this L? So the first remark is that at any point where F is continuous and locally bounded, no, is continuous, sorry, then L exists. And so somehow, if you're continuous, then you're actually subdifferentiable, and then there is a V. Let me remind you, it was lower semi-continuous, so it's just continuity in one side. And this just follows from Anbana. So the only question is whether you are continuous, and if yes, there exists a V. It's automatic. And then one remark is that at any x in the interior of the set where f is finite, okay, where f is, so I'm assuming I have a point in the interior, so I can move around and still be finite. And I also assume that f is locally bounded at x, so it's locally bounded in the neighborhood, then it's continuous. And so there exists an L. So that's somehow, I think, essentially the best. Well, I mean, there is a third result that says that F is subdifferentiable on a dense set. But as I told you, it's not very, very useful because a dense set can still be very small. Anyway, so it's just to tell you that it's just the problem of continuity or F or T that we have to look at, and if we can find a density for which it's continuous, then actually there exists a potential V theta, and we've solved our problem. So recently there was a theorem by a chemist and mathematicians, so it's Suter Eta, it's a big team of 1, 2, 3, 4, 5 people, 24, who applied this reasoning. So you work, so it's in 1D, so you put particles on the unit circle. Okay, so you work on a compact set, no boundary, say unit circle, it doesn't have to be length 1 or length 2 pi or whatever. So you put particles on a curve, if you like, n particles, and then you take a row, such, so row, with square root 4 in H1, and the only thing you add is that 4 is strictly positive. Okay? Then there exists a V. And this V is actually in H minus 1. This theorem works with a W or without a W. W nice. W in T plus infinity, L infinity as before. Okay, so you see, if we work in dimension 1, where H1 is special, of course, because all functions are continuous, So if we work in dimension 1, then we can solve the problem, we can find the potential. The potential is not going to be too nice, it could be a delta measure, for instance, it's in h minus 1. But we can find a potential that will reproduce, even with a W, or no W, whatever, any strictly positive density. I mean, it's very special because it's one dimension, but why does it work? Well, it's just that this makes rho in the interior. Okay, so the proof is just a few lines in a way. So you take x to be h1. So you assume that rho itself is in h1. Square root rho must be in h1, but when rho is strictly positive, it's the same to ask that rho is in h1 or square root rho is in h1. So you work in h1, which is why v is in h minus 1. Okay? You work with h1, and then you show, I mean, it's clear, I mean, everybody is continuous now. So if rho is strictly positive, then it cannot touch 0, and then if I slightly perturb rho in h1, which are also continuous, then the square root will stay in h1, and so you are in the interior, you apply this theorem, and you get a potential. So as far as I know, it's the only example where the problem is essentially solved. Okay? And it's completely expected that rho will always be strictly positive. I'm not sure it's been proved that rho is strictly positive for fermions for any W, but I think it's true. It's probably easy. And so you see, on a circle, the problem is solved. But we don't know how to do it on the whole line, we don't know how to do it in any dimension. Okay. So you see where we are, so we have a way of finding a dual potential, but we don't quite know if it exists or not. And so what Lewin said, in 83, he said, let's forget about this potential, and let's really work with a dual functional and really express everything and with the Legendre transforms, and let's not try to find a potential V. Okay, I wanted to insist a lot on this presentation of DFT with the potential because it's the historical one, and also because if you don't look at ground state, I don't know any other way. So if you look at excited states or if you look at the time-dependent problem, then I don't know any other formulation than what I've done, than the one on the blackboard. Okay, you can easily generalize this to excited states or to the time-dependent equation. But for ground states, we have this convex analysis business, and so we can go further and do things in a completely different way. Okay? And so Lewin said, and that really had a huge influence in chemistry. It really gave a hint on how to construct functionals. So he said, let's not try to find V theta, but let's just try to compute the En of V using the Legendre transform. So we already have a very nice formula, here it is, I write it again. En of V is the infimum over rho with the square root rho in h1 of f of rho plus integral rho of V. You see? So, of course, we don't know f of rho, but if you come up with a simple approximation of f of rho, then you get an approximation of E of V. And this is called orbital-free DFT, in the sense that the variable is rho and there is only rho. So the idea is that you replace f by an approximation, and then you solve this problem and you find an approximation of the n-body problem. Example, Thomas Fermi. So that's for electrons. Then your f of rho, you approximate it by the Thomas Fermi constant, rho to the 5/3 plus 1/2 rho of x rho of y divided by x minus y. Okay, that's an approximation of f of rho. You take this, you replace f by this, and then you get the Thomas Fermi problem that Lewin explained yesterday. That's one approximation. So you see, it's not so bad, right? Because we know that this universal f exists. We don't know what it is, but if we find approximations of f, then we can go further. Now it's not quite in the spirit of having a non-interacting problem. And so people, they actually use Cochan, which is slightly different, and starts by writing a tautology. So let me write this tautology for you. E n of v. So E n of v is here, that's the infimum of rho of f of rho plus rho v. Very good. And now I'm going to insert by hand the non-interacting problem. I want to compare this with the non-interacting problem, so I just write infimum over rho of t of rho plus rho v plus f minus t of rho. Really a tautology. Okay. But then I go backwards in all the manipulations. So T of rho is the minimum of the kinetic energy of gamma. Okay, so you see that I can write this as the infimum over gamma now of the trace of the sum minus Laplace xi gamma plus rho gamma, right? Because I can take the gamma that works for that rho, and then they all have density rho, so I have integral rho gamma v plus f of rho gamma minus t. Yeah, I wanted to make it fit on that blackboard, but okay. Should I write bigger? Thank you, Robert. Let me write the final manipulation. So E and V. So I can write as the infimum over mixed states gamma of kinetic energy of gamma, so the sum of minus Laplace xj gamma plus rho gamma v, okay, and then plus f of rho gamma minus t of rho gamma. So, stupid manipulation so far. But when we write everything like that, then we see the non-interacting problem coming. So there we are. So there are two formulations of DFT. The orbital-free DFT and the Cochan DFT. So Cochan, you introduce the kinetic energy, you rewrite it in terms of some gamma, and then you correct that by f minus t. It's useful. So what have we done? You see, the first line is the non-interacting problem with v, not v tilde. And the second line is a function of rho. So actually, if there is a minimizer for this problem, okay, then maybe I continue here because I have to stop in 2 minutes. So if there exists a minimizer gamma for this problem, and if f minus t is differentiable, we don't know f minus t, but imagine we know and it's differentiable, then we will find some equation. We will have to sum minus Laplace plus v plus the d over d rho of f minus t times uj equal omega j uj. Okay, because that's a function of rho is here. And so the gamma will be like this. Right? And I mean, if my B state is pure, then it's a Slater determinant, and I will have to fit. So that's V tilde. So V tilde is here. I can also say that V tilde I will get if I find a minimizer for this problem, and I can differentiate. Okay. Good, and that's Cochan. And so what do you do in practice? Now you find approximations for f minus t. And so let me finish with this. So in practice, you replace the unknown f minus t of rho by an approximation. This approximation is always taken in the form of first the direct term, which is w of x minus y, rho of x, rho of y, dy, dx, dy, which is called the direct term. And we can always decide to put this guy inside. And then plus the rest, which is called the exchange correlation energy of rho. So, I mean, the exact exchange correlation energy is just this minus that. And then in practice, you just invent formulas for the exchange correlation energy. You plug it in here, and you really get a non-interacting problem in the sense, I mean, it is interacting, but in the sense that you have here a linear problem, and then a highly non-linear function, but only of rho. And that's the way that you solve this quotient problem. And so 1 minute, how do you find these approximations? So Purdue invented what he called the Jacob's ladder of DFT. If you type this on Google, you will find lots of drawing of this ladder. Okay? And so it's a ladder like this, which goes to heaven, and heaven is chemical accuracy. Okay, and so the ground floor, so the ground is when this is 0, so that's the simplest approximation, so that's reduced Hartree-Fock. That Philippe also introduced yesterday. Okay, so Hartree or reduced Hartree-Fock is really down to Earth. And there's even underground. So underground is orbital free DFT. Okay, that's very deep. Okay, because it's too simple. I mean, Thomas Fermi and so on. It's very hard to get good approximations on F. So. And so you start with reduced Hartree-Fock, and then you try to invent functionals of the density that will well describe this exchange correlation. And so the first ladder is local functionals, namely, you take an integral of a function of rho of x dx. Okay, so it's local, it only depends on the value of rho locally, and then you average. And the most famous is ADA, okay, which I'm going to discuss tomorrow. And so the next step are what are called GGAs. So generalized gradient approximations. What are GGAs? GGAs is when you take a function that depends on rho, but also gradient of rho. So somehow, it's not the same function, of course. So you take into account the variations of rho locally. And here you have the famous PDE, for instance. So you just replace this unknown guy by a function like that, and you solve this problem. Okay? And then you have meta-GGAs. Well, maybe I don't put it because I have only two scales left. Okay, so meta is when you take several derivatives. It's already more complicated. The next step is a hybrid. So hybrid functionals are when you also put some exact exchange, meaning that you compute the one particle density matrix of your gamma here, and then you put the exact exchange of that gamma, which has nothing to do with the exact exchange of the two problems, but hybrid, and here you find B3 lip, which I mentioned yesterday. For instance, there's also a version of PDE here. And then, some of the goal is to try to find good non-local functionals. But so far they did not find any very, very good non-local functionals. And of course you see it goes like this forever, because you can always complexify. But there's a natural way to complexify, namely introduce more and more gradients of rho, to try to introduce non-local terms, so as to make your model more and more precise in order to attain heaven, which is chemical accuracy. And tomorrow I will explain what LDA is. LDA is really the first, people call it the mother of all approximations. And we managed to justify LDA recently, so that's what I will describe tomorrow. Thank you. It's from the Bible. It's not Purdue.
Questions? So maybe I ask one more. You mentioned this density, right? And you actually also mentioned that it doesn't mean much, just
Yes.
the sense. But is there more now, actually, something more quantitative?
So I
There
have
are
this,
other notions of quantifying.
yes. So I have this student, Louis Gary, so he was looking on a compact set, and he proved under some assumptions, I don't remember, that it's negligible. And so it's a union of compact sets, countable union. So it's dense, but probably very small. Okay. But the main problem is that you don't know where to find V. And I think if you try to find V in NP plus N infinity, it's not a good space. So you will get an extreme, it's going to be dense, but you will get an extremely small set. And so the real question is, for which V can I give a meaning to the n-body problem? And definitely the positive part of V can be very wide, and must be very wide. If rho has compact support, V must be infinite outside of the support. Okay? So somehow this here is not good, that's clear. And that's why, it's still dense, but probably very, very small. And so the question is, what's the largest possible class of V? And then maybe for such a class, it's better. And you see, in one dimension, you have to allow measures, which is probably not surprising. And then you can solve it. So some of the real question behind is, for what potential the n-body problem is well defined? What kind of very wide potential?
Thank you for the talk. I was wondering if your valuing is easier somehow. It's like power of some distance, which makes the problem less complicated. Then do we have any chance to know what the ground state is?
For sure, there are some completely integrable systems where you can do more. For instance, in 1D, if W is 1 over x squared, you can actually compute everything. But there are very few such systems. And so, higher dimension, I don't even know idea where W is. So in most cases, you can't hope to compute anything. The real side, it's really too hard. In 1D, there are examples. But in one dimension, there are examples of very specific W's for which you can actually compute the interacting sum. But for general W's and in higher dimensions, it's very unlikely. But let me insist on the fact that here, in a way, it's the non-interacting problem which is the main question. Because we've got the interacting, okay, it's very wide, but we want to know how the non-interacting problem can represent such a wide object. And so, even here, take W equal to 0, there are lots of questions which are open.
Yet this potential is a bit unclear, like
The V theta, yes?
we don't know what that is, so I don't know how that's complicated.
If you look at the classical case, so you do not put any Laplacian, then V theta, and then you actually end up getting an optimal transport problem. Everything I said is just an optimal transport problem. And then V is the contour of each potential, so it has some meaning, the V theta. It has a physical meaning in a way. That's the potential that can reproduce this density rho.
I made a quite naive question. So you want to look for a non-interacting problem which kind of has the same density as the
Yes.
but you're looking for one specific, so for a single util for all the particles. Would it make sense to look for
maybe there's more chance, but then you lose the fact that they must be undistinguishable, these particles. So somehow you're putting labels. Why not? Why not? You could do that. I don't think it's much easier.